In this problem, we want to find the singular value decomposition for the matrix 5, 1, 10, negative 2, 10, negative 2. So the first thing we want to do is we want to find the transpose of A multiplied with A. And here's the matrix setup. The transpose of A is negative 5, 10, 10, 1, negative 2, negative 2. So when we do this multiplication, we're going to get negative 5 times negative 5, that's positive 25, and then 100 and 100, so it looks like it's going to be 225. And then on the wings, we're going to get negative 5 times 1, 10 times negative 2, 10 times negative 2. So for that, it looks like we're going to get negative 45. And then we're going to get the same inner product when we do the other wing, and then the last diagonal is 1, negative 2, negative 2, and we're going to essentially square that. It looks like that's going to be a 9. So now that we have that, we want to find the eigenvalues and eigenvectors. So we will take our matrix that we just got, and then we will subtract that, subtract lambda I from that. So let's get this set up, and we got a minus lambda, and then a 9 minus lambda, and then everything else stays the same. And so this thing is going to be a quadratic polynomial in lambda. So we're going to start off with multiplying the diagonals. We got a 225 minus lambda times 9 minus lambda, and then 45 squared. I think 45 squared is 2025. And so this thing, if you multiply this out, it should turn out to be lambda times lambda minus 234. And if we set that equal to 0, we're going to have our eigenvalues. So it looks like from the largest number first, we got lambda is equal to 234 and lambda is equal to 0. So we have our eigenvalues. Now we want to find our eigenvectors. Now to find our eigenvectors, what we want to do is we want to set up our matrix minus lambda I with lambda is equal to 234, and we're going to also do the same thing where lambda is equal to 0. And from here we should solve for this the null space for this matrix, and we're going to get our eigenvectors. So if we go ahead and do that, we will get this should be equal to negative 9, and this should be equal to negative 225, and then this is all a multiple of 9, so we're going to get I think if we reduce this and multiply the top row by negative 9, or divide by negative 9, we're going to get a 1 and a 5. And then if we go ahead and do the row operation here, multiply this by 5, we're going to get negative 5. We're going to get 0 and 0 here as well. So here's our reduced matrix. We will look at this and say that x2 here is a free variable, and then x1 is going to be minus 5x2, and so our eigenvector will be minus 5 comma positive 1. So if we go through the same moves over here, we should get our other eigenvector. So we have 225 and 45, 9, 45. Again, do some reducing, and switching if you need to, and I think this is going to turn out to be 5 and -1, and then that would wipe out the whole second row, and then another free variable at 1 at x2, and then x1 is going to be positive 1/5. Now, since this is a multiple of x2, we can just imagine multiplying this by 5 just so we have nice whole numbers. If we multiply this whole thing by 5, then it might make things a little bit easy for us. So multiply by 5, that will make this into a 1 and make this into a positive 5. So I think these are nicer vectors to deal with, and now that we have that, we're pretty much ready to find our V vector or V matrix. Before we do that, let's find our sigma matrix, and we need our singular values. So our singular values is going to be, one of them is 0 and the other one is the square root of 234. I don't know if that simplifies, so maybe we'll just leave it at that. And these will be the exact values in a diagonal. So notice that our matrix, our sigma matrix, is the same size as our A matrix. And so we fill in the diagonals, and then everything else would be zeros. So this whole bottom row, which was added from a square matrix to make a matrix of the size the same as A, will have to be equal to 0. Okay? And so now we continue and construct our V matrix, and to do that we look at our V vectors for eigenvectors that we got. So V1 is equal to -5 and 1, and so the square root of that looks like it's going to be the square root of, or the magnitude of that looks like it's going to be the square root of 26. And if I notice that V2 looks like it's the same thing, so I don't have to recompute that. And so this is also equal to the magnitude of V2. And then now we can just divide everything by square root of 26. So I'm going to take V1, that's a -5 and 1, and for each of them I'll divide by the square root of 26. And then likewise I will take the 1 and the 5 from V2, our second eigenvector, and I'll divide by the square root of 26. And so we have our V vector. We want our VT, the transpose, but this also happens to be the same as the transpose, so I think we can just say this is equal to VT. And then we'll work that out later. So now let's find our U matrix. And for our U matrix, what we want to do is we want to take our eigenvalues or eigenvectors and multiply it by our A matrix, our original A matrix. Now we can use the normalized vector, but I think it's better to use the original vector so that again we're dealing with nicer numbers and not have to worry about square roots, because we're going to have to find the magnitude of that anyways. So even if you used your normalized V vector, your answer here will probably not be a vector, a unit vector, and so you're going to need to divide by that quantity anyway. So why not deal with -5, 1 instead of -5 over root 26, 1 over root 26. So the V that I'll choose to multiply here is going to be -5, 1. And when I do this multiplication, it looks like for the first slot I'm going to get a 26. For the second slot I would get a -50 and -2. So -52 and the same thing for this last one. What's the magnitude of that? Well, after some computation, you can probably use your calculator or whatever and get the magnitude to be 78. So we have our first unit vector, our first column for our U matrix. And remember, since we have a 3 by 2 A matrix, our original matrix was 3 by 2, we want your U vector, your U matrix, to be a 3 by 3 matrix. So we're going to divide by the magnitude, and then our vector is, well, if we just leave our vector like this, that's fine. I think we can also multiply that out and simplify it. So this simplifies, if we divide by 78, I think this will divide into a 1/3. The second one will divide into a 2/3, and the same for this one. And now we have the first column of our U matrix. Now if we do the second one, our second our V2 vector was 1, 5. So put 1, 5 here. If we do this multiplication, you'll see that something kind of weird is going to happen, and it almost made sense because we have our second eigenvalue to be 0, and in this case it turns out that the eigenvector is part of the null set. So what we need to do is we need to find another way to get the two other columns for our matrix. So in order to do that, what we're going to try to accomplish is just the relationship that this has to be an orthogonal matrix, which means the dot product of our U1 vector and some random vector x1, x2, x3 has to equal to 0, and then we're going to try to solve for x1, x2, and x3. Our vector is our U vector is 1/3, -2/3, -2. We can, I think, simply use, since the direction or the magnitude doesn't matter, we're just more focused on the direction. So instead of the 1/3, -2/3, -2/3, I'm just going to multiply everything by 3 and go with a 1, -2, -2. So let's take our U vector, or let's say modified U vector. So let's maybe put a prime there and say this is a 1, -2, and -2. And so when we take that dot product, we're going to get a 1, -2, and a -2. So we want to solve for this, and if we imagine this as being a system where we had 3 equations and 3 unknowns, and then we do the row reducing and the last 2 rows happen to be zeros, we can think about this as having a free variable in x2 and x3, and then solve for x1. So if x2 and x3 are free variables, then we can just think about that as a free variable in x2, and so this will be a 0 in x3, a 1 in x2, and then if x3 was equal to 0 and x2 was equal to 1, then x1 is going to equal to, it looks like it's going to equal to +2. Okay, so again, we're just solving for this this equation here, and we're setting x2 and x3 as free variables. And so if we do the same thing here, where x3 is free, we'll have a 1, and x2 is not counted in this one, and then our x1 is going to be again a -2 brought over to the other side. It'll be a +2x3, so we have this as well. Okay, so now we have 2 new vectors to work with that are perpendicular to U, or that are perpendicular to U1, and so we're going to go with these 2 vectors. Now notice that they're not orthogonal, If you take the dot product, we're going to get dot product is 4. So they're not orthogonal, they're not normalized. And so what's the way to orthogonalize and normalize these vectors? We can use the Gram-Schmidt orthogonalization process and then do it that way. Now we have two choices. We can either begin with this vector, normalize this vector, and then find the orthogonal projection using the second vector, or we can start with W3 vector and then find the orthogonalization of the first vector. In either case, we should get a U. So at this point, it's good to point out that the singular value decomposition of a matrix may not be unique. It's not uniquely determined, and so in this case we have two possible answers for U, for the matrix U. So let's begin finding our U matrix by letting this be our first vector. And if we do that, I went ahead and did all the work here. If we do that, if this is our original vector, we're going to go with this as our U2. U2 is going to be the normalized version of W2. And then the Gram-Schmidt process, the formula says that if we want to have W3 part of it, we're going to have W3 minus, and then here's a scaling constant that was built from a projection, and we're going to project it onto U2. And then so this vector projected onto U2 minus subtracted from this vector is going to give us our perpendicular vector to U2. So the work that's being done here is that we have 2, 0, 1 minus, and this dot product combination is going to give us 4/5, and then we have 2, 0, 1, and then we get this vector. Now this vector is not necessarily a unit vector, so we want to make sure we make it into a unit vector and normalize it. So we divide by an appropriate value, and so if we do that and then I rewrote the vector so that it has whole numbers. We have 1 over 45, and then 2, negative 4, and 5. So that's our U3. So remember, our U1 was 1/3, negative 2/3, negative 2/3, and given our U2 in this case as 2 over root 5, 1 over root 5, and 0, and then we just found our U3, which is 2 over root 45, negative 4 over root 45, and 5 over root 45. So this is one possible answer for our U matrix. If we had chosen W3 to begin with, then we would have had a different set of column vectors for your matrix U. So here's the result for that. If we went with W3 as our U2 matrix, then our third matrix, or our third vector, is going to be the projection of W2 onto W3 or U3, and then this is what we would get. It's close, but it's not exactly the same. And so if we take a look at our third unit vector in our third column, we see that it's a little bit different, and likewise our second column is a little bit different. So we have a different value for our U matrix. So when they say that U is not uniquely determined, actually they say U and V are not uniquely determined. This is what they mean, and so there's possible choices for them, and I guess you can have the option to do this if depending on what you think would be better, but I think either of these would have amounted to the same kind of work, and so there's no real advantage of one over the other. All right, so this is our second example for a singular value decomposition, and I hope this helps.